Okay, 2.12, we're asked to find the eigenvalues and eigenvectors for the spin operators for Sx and Xy for a spin 1 particle. So these are 3x3 matrices. These are given. I made another video of how we get to these matrices, so watch that if you're curious. But as far as getting the eigenvalues, if you remember or if you've learned how to take the determinant for a 3x3 matrix, this will be pretty easy for you. If not, then this might be a little bit more difficult. But reminder, to get the eigenvalues, you take the determinant of your operator, so I'll say Sx, minus lambda times the identity matrix, and set that equal to 0, and then solve for lambda. So we'll go ahead and do that. So we'll make our matrix here. To make things a little bit easier, so I don't forget this h bar over root 2, I'll go ahead and multiply that into the matrix as I go here. So first of all, we have 0. Remember to do the minus lambda on the diagonals. So it'd be 0 minus lambda is negative lambda. Our 1 goes to h bar over root 2, and 0. And then h bar over root 2. This is on the diagonal, so remember the negative lambda. And then h bar over root 2. And then we have a 0 and h bar over root 2. And again, we're on the diagonal, so negative lambda. And set that equal to 0. So in order to take the determinant of a 3x3 matrix, what you do is first you take the upper left value. And this is going to be, it's going to go in order, it's going to go plus, minus, plus, if you remember that. And it'll alternate. So first we're going to take the positive, not the positive value, but we're not going to make this positive because negative and a negative. I don't know if I'm making any sense. We'll see when we get to the second value. So this is going to be negative lambda. And then you cover up the column of the value you just took. So we took that value there, so we cover up that column. We're also always going to cover up this first row. And now here you can see that we're left with this 2x2 matrix. And we just take the determinant of a 2x2 matrix at that point. So it's going to be the diagonals minus the diagonals. So we have negative lambda times negative lambda. That'll be lambda squared. Minus this diagonal here. So that'll give us h bar squared over 2. Oops, forgot the minus there. All right. So then we move on to our next column here. And again, so this is plus, minus, plus. So this is going to be minus here. So we do minus h bar over root 2. And now we cover up this column here. If I can do it. Cover up this column here. And we're left with this matrix here. So we do the diagonal here. So we have a negative. I'll do h bar over root 2 on the left, and then lambda there. Minus, and then that diagonal is going to be 0. So we'll be left with that. Okay, so it's going to be plus, and then 0 times anything is 0. So I'll just write plus 0. Okay, we'll go ahead and multiply these in. So we'll have a negative lambda cubed plus h bar squared over 2 lambda. And then here we have a minus and a minus. It's going to make a plus h bar squared over 2 lambda. And this is still going to equal 0. All right, so now we can combine like terms. We can also pull out a lambda. So I'll pull out a lambda here. So I'll pull out a lambda, and we'll be left with a negative lambda squared plus, this is going to be 2 of these h bar squared over 2's. H bar squared over 2, and we already factored that lambda. Well, that's going to be 2 of these h bar 2's over, what did I just say? 2 of these h bar squared over 2's. The 2's cancel out, though, so that'll just be h bar squared. Hopefully you see where that came from. Equals 0. Okay, so in order for this to be true, either lambda has to be 0, or this term has to be 0. So one option is just that lambda is equal to 0. The other option is that negative lambda squared plus h bar squared is equal to 0. And then we can just move the negative lambda to the other side. So we have lambda squared equals h bar squared. And then take the square root of both sides, and we have lambda is equal to plus or minus h bar. So our values of lambda, we kind of already knew, because they're the eigenvalues for a spin 1 system. lambda is going to equal negative h bar, 0, write that very well, negative h bar, 0, and positive h bar. Okay, there's our eigenvalues. Okay, to find our eigenvectors, remember that if we apply our operator here to some arbitrary unknown vector, and they're going to have 3 terms because it's a spin 1 system. So just give it 3 variable names. You can use x, y, z. I'll use a, b, and c. And if you apply the operator to that vector, what you should get back is your eigenvalue. We'll start with h bar. And then our vector back again. So a, b, and c again. Okay? So let's go ahead and replace this sx with our actual operator in matrix form. So we'll have h bar over root 2, 0, 1, 0, 1, 0, 1, 0, 1, 0. Okay. So first thing that you can see is that the outside terms don't match. So in order just to make things easier, so we can kind of just look across each row to see what our a's and b's and c's are equal to, let's go ahead and make them equal. So you can either multiply across root 2 both sides, which would put root 2 into each one of these terms. That's one option. Or you can multiply in 1 over root 2 into this matrix here. Either one's fine, doesn't really matter. I'll do the second one. So we'll have h bar on the outside. We'll have 0, 1 over root 2, 0, 1 over root 2, 0, 1 over root 2. This way might be more writing, but 0, 1 over root 2, and 0. Times our a, b, and c equals h bar, a, b, and c. Okay, so now our outside terms match, so now we're looking good. So now let's go ahead and do this matrix multiplication. So we're going to have h bar still on the outside. We're going to have a times 0, 0. We'll have b over root 2, and then c times 0 is 0. Our second row is going to be a over root 2 plus c over root 2. And our third row, again, is going to be b over root 2. Write that very well. B over root 2, okay, equals h bar, a, b, and c. Okay. Now we can see that a is equal to b over root 2. B is equal to a over root 2 plus c over root 2. And c is also equal to b over root 2. So c is equal to a. All right, so I'll keep that there. Yeah, I'll write over here. So there's several values that would make this true, but less values that would make the normalization equation true. So remember, a squared plus b squared plus c squared will equal 1 if this is a normalized vector. So we'll go ahead and go with that. So we're going to condense this down to one variable. We can use b, because we know that a is going to be in terms of b. So a is going to be b over root 2, square that, plus b is just b. And c is the same thing, b over root 2, and we'll square that, and that should equal 1. So go ahead and square these here. We'll have b squared over 2 plus b squared plus b squared over 2 equals 1. So we have 2 of these. So then the 2's will end up canceling. It would be 2 b squared over 2. 2's cancel out. So we'll be left with just 1 of these. So I'll just keep 1. And then we'll have 2 b squared equals 1. B squared equals 1/2. And b is equal to 1 over root 2. So I'll write that over here. So b is equal to 1 over root 2. And now that we know that too, we can put that in for our b here. So we know that c is equal to a is equal to, so b is 1 over root 2 over root 2. And that's going to be equal to 1/2. A is equal to 1/2, C is equal to 1/2, and B is 1 over root 2. So that means our eigenvector would be, for our first eigenvalue, so that's our 1 state, is going to be equal to our A is 1/2 for our 1 plus 1 over root 2 for our 0 plus 1/2 for our -1. I ran out of space there, but got it. All right, and if you were to square all the terms that add together, you can see that that is normalized. All right, so that is for for h bar. Now if you do r0, so I'll just do it here. Again, you can see that our outside terms aren't the same, so we could multiply in the 0 to make all these terms 0. Just so I don't have to rewrite things, we'll just remember that. So that means that we know that b is equal to, I'll also erase those. Those are now old. B is equal to, b over root 2 is equal to 0. We know that that's going to be 0. A over root 2 plus c over root 2 is going to equal 0. And we already know that b over root 2 equals 0. We already have it there. So again, with our normalization, if we can condense this down to one variable, so we know that b is equal to 0. If b over root 2 is 0, then we know that b has to equal 0. So we know that b is equal to 0. All right, so then for our normalization term, if we were to, let's go ahead and multiply both sides by root 2. So that makes a plus c equals 0. That doesn't really look like an a. A plus c equals 0. And that means a is equal to minus c, or c is equal to minus a. All right, so our a is going to just be a. We'll take a as our variable we're going to keep. B we know is 0, so we can leave that off. Plus c, and we know c is going to be negative a. And that's going to equal 1 if it's normalized. The negative sign doesn't matter because it's the absolute value. So that's going to end up being 2 a squared equals 1, which means a squared equals 1/2, and a is equal to 1 over root 2. All right, so we'll write that here. A is equal to 1 over root 2. And if a is equal to 1 over root 2, we know that c is just the negative of that. So that means c is equal to negative 1 over root 2. All right, so that one wasn't too bad. So that means our 0, a little bit more room here, is equal to, our a is 1 over root 2 for our 1 state. There is no b, that's 0. So then our c would be minus 1 over root 2, negative 1. And again, you can see that that is normalized. So lastly, we got the 1, we got the negative 1, or we got the 1, we got the 0. Now we need the negative h bar. Okay, so now we can see that our outside terms, again, are not even. So if we can distribute this negative in here, we have negative a, negative b, negative c. So now we can see that negative a, well, let's just flip the signs here. So we'll make these negative. So a is equal to negative b over root 2. B is going to equal negative that, so negative a over root 2 minus, don't forget to distribute the negative, c over root 2. And c is equal to negative b over root 2, which is the same here. So I'll say c equals again. Okay, so same thing as the first one where we have everything in terms of b here. So a is going to be negative b over root 2 squared plus b is b, so b squared, plus our c is also going to be negative b over root 2 squared. And this is going to end up being b squared over 2 plus b squared plus b squared over 2 equals 1. Again, these will end up combining to be 2b squared over 2. 2's cancel out. So we'll keep one of those terms, and it'll end up being 2b squared equals 1. B squared equals 1 over 2. And b equals 1 over root 2. All right, so I kept these here, but get rid of that. So b is equal to 1 over root 2. And again, just like the first time, we will plug that in here. So c is equal to a. A is equal to negative. Our b is 1 over root 2. And then over root 2 is equal to negative 1/2. All right, so a equals negative 1/2 and c equals negative 1/2. All right, so that would make our final vector, our negative 1 state, equal to a is negative 1/2. Typically, typical convention is to keep the a term positive and real. So if we flip the signs of everything, which is legal to do because we can manipulate the phase of c, and so it would be equivalent. As long as we flip all of the signs, the state is still equivalent. So let's go ahead and do that. So let's make this a positive 1/2 for 1. And then this is going to turn to minus. So let's just write here. So those become positive, this becomes minus. So minus 1 over root 2 for the 0. And then plus 1/2 for the negative 1. And those are our 3 eigenvectors. All right, I'll go ahead and do the SY in the next video. This one's getting a little bit long. It's going to be very similar to this one, though, but I'll go ahead and cut it here.